to this done. Great. Okay, so today is Tuesday, the 7th. We're a little bit more than halfway through the semester. I don't know if that's a precise amount or we're close to it. Um, but the semester always kind of wraps up before you expect it, I feel. Now I've made some changes to the class Canvas site. I'm not sure if anyone had the chance to look at this, but I hope that I made it a little bit more user friendly. I gotta switch to the student view and then I will share my screen so you guys see what I see. I added a couple of links so that it's a little bit easier to bounce back and forth through things. So for instance, right now, if you go to our class homepage, what shows up at the top is going to be the month of October. So we are today, the 7th. You've got the PowerPoint or the slide deck, the PDF of that same slide deck, basically all the material that we're going to be covering. So we have 2 weeks from Thursday until exam number two. Um, I've got a link if you want to go back and look at older stuff that goes to September. And same thing goes, I've added these links at the top of those pages so that it's hopefully a little bit easier and more clear for you guys to navigate. Now, today I'm going to jump right in and we are going to be talking about drawing molecules and what they look like in 3 dimensions. And that's the really important part of all of this is change my share. I have not, and I'm about to down. Okay. Um, the question is really what space does something occupy? Um, whenever I draw a molecule, whenever I draw like CH4 and I draw it like this, and actually, this is going to be a good opportunity to kind of go through and practice drawing molecules and kind of going through those steps. If I were to draw CH4, my first step is going to be to identify the elements or atoms and how many of them there are. Well, for CH4, there's 1 carbon and 4 hydrogens. Done. The next thing that we need to do is come up with the total number of electrons in this molecule. Well, for carbon, we've got 4 valence electrons, not total electrons, but valence electrons. The valence electrons are the ones that we care about because valence electrons are the electrons that are involved in sharing or donating between different atoms. We've got 4 hydrogens. Each hydrogen rolls in with 1 valence electron. And since we have 4 of them, we're going to say 4 times 1. So we've got 4 electrons there. 4 plus 4 equals 8. Great. Now, when we draw this structure, we'll then go on to identify our central atom. And if you're looking at this and you're like, where are these numbers coming from? Well, I'll jump ahead to show you the reference slide that's good for you guys to keep in mind. This one right here, this shows our Lewis structures or our Lewis dot structures of carbon and hydrogen respectively. Or respectively. Another place that it's coming from is the periodic table and remembering kind of where things are. Do you have to memorize where things are on the periodic table or memorize information in the absence of the periodic table? Not really, because you'll have a periodic table on your exam. Um, but there are some elements that the more that you draw them, it becomes a little bit more of muscle memory of sorts. So this is where I got those numbers from. 4 hydrogens, each hydrogen having 1 valence electron and 1 carbon with 4 valence electrons. So that gets us our 8. So we've got our 8 total valence electrons. The next step is going to be identify our central atom. Okay, well, our central atom is either the farthest left on the periodic table, unless it's hydrogen, or our central atom is the least electronegative, which, I mean, you don't have the electronegativity values here, but alternatively, many times whenever the formula is written, it's just the first element that's written. So C of the CH4. So our central atom is carbon. We're going to write our hydrogen, 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 hydrogen outside of that. Then I'm going to draw a line to represent the bond that connects each one of these. Could anyone add to the chat how many electrons are represented by that bond right there? Two. It's a shared pair of electrons. Okay, so two electrons. So how many electrons do I have basically represented in this structure total? Great. I have eight. I had eight to work with. So basically, this is my structure. Now, with that in mind, whenever we look at this structure, um, is everyone familiar with a graph where you have the y-axis and the x-axis? Could you give me a y or an n if you're familiar with plotting something on an x and y axis? Okay, cool. Now, with that in mind, when you look at this, I want you to think about this as this is two dimensions. Can everyone give me a 7 in the chat if they understand that, yeah, if you plot something on here, it's two-dimensional? Okay. Now, if we were to look at this and say, well, two dimensions, that means one dimension is our height, and the other dimension is basically our width. So those are our two dimensions. Has anyone ever played the regular Nintendo that came out in like 1986? Give me a Y or N to the chat. Hmm, okay. If you've never played that, I'm sorry for this example, but basically the regular Nintendo, the term that's used for it is slide or side scroller. It's a side scrolling video game. So you watch Mario in one position, or heck, you can replace this with any number of other video games. You watch Mario and he runs from one side of the screen or one side of the map to the other side of the map. Could everyone give me a Y or an N if they understand that idea? Okay. So Mario is a good example of a two-dimensional figure. Now, Joel Gray, I walk around in the world and visually I'm a three-dimensional figure because I've got height, I've got width, but I've also got a third dimension of depth. Could everyone give me a Y or N if they understand that? Okay. Now, with that in mind, this figure right here, could you tell me, is that a one-dimensional figure, a two, or give me a two-dimensional or three-dimensional? If it's a two-dimensional figure, add a two in the chat. If it's a three-dimensional figure, add a three in the chat. And I'm asking as I've depicted it, as I've drawn it. Yes, you're absolutely right. This is a two-dimensional figure. Now, this CH4, when it exists in space, do you think it's a two-dimensional figure, so it's flat? Or do you think it's three-dimensional and maybe has like depth? Great. It's a three-dimensional figure. Now, with that in mind, when we look at this figure, we want to be able to kind of visualize that transition and kind of speculate, look at that and be like, huh, what do I think that looks like in three dimensions? Because if we can know what something looks like in three dimensions, we have more information about it. For instance, and I always like to think about this, going back to the Mario example, we see Mario running in one direction. So when we see Mario going from the left side of the screen or the left side of the map to the right side of the map, we only see one side of his face. And I know, just bear with me, I know that when he turns around, you see the other side of his face. But if we're watching him going the left to the right, we only see the right side of his face. He might have a Mike Tyson styled face tattoo on the left side of his face that we'd never see because we don't have that depth. We don't have that visual. We don't have that different angle. So when you can see something in three dimensions, you know more about it. Now, what we're going to do today is work on taking figures like this, structures like this, and converting them into three dimensions. And that is basically coming up with a molecular shape or a molecule shape. So could you give me a One in the chat if you follow how this goes from our drawing of Lewis structures to visualizing something in 3D, and a two in the chat if you're like, I don't really see the connection. Okay, I'm seeing lots of ones. I'm happy to see that. We're kind of building on that two-dimensional figure is the objective today. So, what needs to be known in order to kind of master this or feel really confident about this material is this slide right here. And just as a little bit of a reminder, the neutral atoms on your main group elements, which are all depicted here, you can deduce the number of valence electrons they have based on the group or the column that they are on the periodic table. Group 1, group 2. And if you remember, we skip the transition metals, and then we've got our column labeled 13, which is our group 3A. Boron and aluminum are the ones that are in there. They have 3 valence electrons. Carbon, silicon have 4, 5, excuse me, 6, 7, and last but not least, our noble gases, all except helium, have 8 valence electrons. Now, another way to visualize that is by looking at the number of bonds that these elements like to make. Now, if you look at this, you might say, oh, well, okay, Hg, what is that? Well, Hg is mercury. We don't really talk about mercury very much. And that's in large part because we've got enough to kind of consume with these right here. Similarly, what we really kind of focus on, and what we will see more times than not, and I'm going to circle the ones that are maybe the more commonly seen. We've got hydrogen, boron, carbon, nitrogen, oxygen, fluorine, chlorine, phosphorus, and yeah, I mean, silicon's not too tricky. Silicon doesn't have any special rules, and sulfur S doesn't have any special rules. But I'm just giving you kind of a heads up of like what are the compounds or what are the elements in the compounds that we'll see quite often. So if you're thinking, I need to know these, what I would work on is making sure that I know, well, how many valent electrons does an element have? So I'll type that up here, or I'll write that. Number of number of valence electrons and number of bonds formed. Those are the two things that I would say are maybe the most important. So on a scale of, or give me a Y or an N for this. Do you think we're ever going to see a compound where fluorine forms 4 bonds? Where fluorine. What does fluorine like to form? Fluorine likes to form 1 bond. Are we going to see compounds that have fluorine? Yeah. Okay, so I'm seeing lots of no's. You're absolutely right. We're not going to see fluorine form 4 bonds. Are we going to see fluorine involved in a molecule? Absolutely. One good example, CF4. Ooh, what does that look like? Well, you know what? I'll just draw each one of the fluorines. Each fluorine in that molecule is going to look like this. It's going to have 3 lone pairs of electrons and 1 single bond going to carbon. Now, I just want to give you that as a little bit of a heads up. We'll see some displays of this in just a moment. Now, ultimately, CF4, it's probably going to look quite a bit like CH4. What's going to be different is if we look at CH4, how many lone pairs of electrons does each of these hydrogens have? You're absolutely right. Each one of those hydrogens has 0 lone pairs of electrons. So CF4 is probably going to look like this, but with fluorine replacing each one of those hydrogens. Okay, now drawing Lewis structures, we've got that sequence of events that we need to go through. It's important whenever you draw a molecule to think about what is the total number of valence electrons that I have, and kind of frame it as that I have to draw, and where do I place them? So we'll go through for each one of these molecules that we're going to look at, we'll go through and draw the Lewis structure and then we're going to dissect them. Now, the concept for this, or the idea behind all of this, is known as valence shell electron pair repulsion theory, also known as VSEPR theory. So, just double checking, do we have to memorize the Lewis structures? No. In fact, I got that as a private message. In fact, if I were to, thinking ahead for our next exam, what are some things that I would want to put on my note card? Because you get to use one note card. You don't get to use the first exam's note card again. You get to use one note card. So take information from your first exam and be like, okay, what is the information I knew? And what's the stuff that I struggled with? The stuff that I struggled with, I'm going to put that on there. But I would recommend having like a shorthand note of here's how I draw a Lewis dot structure of a molecule. Okay. You do not have to memorize the Lewis structures. And this table right here, I would not put that on my page because essentially you get that information by knowing the number of valence electrons. So what I want you guys to be able to do is to look at P table. Basically, if you could look at the periodic table and produce this, that would be a very powerful skill for you to have. Now, is that going to be an exam question? No, it's not. But will you benefit from being able to do that? 100%. Okay, so we're talking about VSEPR theory. And yeah, it is VSEPR, but it's pronounced VESPER. VSEPR. Um, VSEPR theory is basically a way of looking at central atoms and asking where those electrons are. And this word right here, repulsion. Have we talked about things repelling one another? Yes or no in the chat? We have. Now, what have we talked about repelling one another? We've talked about electrons repelling one another. Now, when I draw CH4, just as my model, I draw it like this. This CH4, I've drawn it in 2 dimensions. I'm going to put a label A and B by these pairs of electrons. Are these two in 2 dimensions? Could anyone give me an approximate degree measurement that they are from one another? Yeah, 90 degrees. And in 2 dimensions, these pairs of electrons are basically as far from one another as they can possibly be. Now, with that in mind, in 3 dimensions, well, let's think about this. And this is, bear with me on this, but could anyone give me an approximation as to the degree measurement from here to here, approximately? Actually, you know what? Scratch that. Go from here to here. What's that measurement? From X to Y. What's the degreeing? Perfect, 180. So then from Y to X, give me a Y or an N. Would that be also 180? Okay. So then effectively from X all the way to X, what would that measurement be? It'd be 0 or 360. Perfect. Great job. Okay. Now, keep in mind, is this in 2 dimensions or in 3 dimensions? Add to the chat. 2. Perfect. So now this is where my drawing skills run into a little bit of a problem. This that I just drew, I want you to visualize that as that's basically coming out of the paper or coming out of the screen. Can everyone say Y or N? I understand that. This third line. Okay, good. That's coming out of it. Now, if something's coming out of the screen, then I'm going to draw this dashed line to indicate, well, going into the screen. Can you give me a Y or an N if you follow that? Okay. So then if I go from here to here, what's my angle measurement of that to that? Great, 180. This is 180. So we're talking another 360. Okay. So I'm setting all of this up because what I'm getting at is these electrons right here will oppose or repel these electrons. They'll also repel these electrons. And you know what? They're also going to be repelling these electrons down here. And so the angle from this to this, from this X or the angle measurement is going to be different. It's not going to be 90 degrees because 90 degrees is when we're on a two-dimensional plane. Can you give me a Y or an N if you follow that? Okay, great, great. This is awesome. Great job, everyone. Okay, now when we look at a molecule like this, we'll start at the top with HCN. HCN is a compound known as cyanic acid. This is actually the compound that is potentially toxic, cyanide. HCN is cyanic acid. Now, with that in mind, carbon rolls in with, let's go ahead and put this Lewis structure together. Carbon rolls in with 4 valence electrons. Hydrogen rolls in with 1 valence electron. Now, does anyone know, and I'll give you a second, how many does nitrogen roll in with? Nitrogen is going to roll in with a grand total of 5 valence electrons. Great job, Victor. Thank you. So what we have in terms of our total number of electrons to draw is 10. Could you give me a Y or an N if you understand, agree with that? Great. So we got a total of 10 electrons to draw. Now, what we're going to do is whenever we're constructing this structure, we've got to put identify our central atom. We've got HCN. So our central atom is not hydrogen, despite hydrogen being first atom listed. Okay. So HCN. Then we've got, okay, well, our least electronegative element, or our farthest to the left. I'm going to jump back. Our farthest to the left is indeed carbon. So we're going to use carbon as our central atom. So that means we just do H and N. In this structure right here, I've drawn a total of 4 electrons. I want to draw 10. And whenever I do that, I'm going to go ahead and put this triple bond right here. How many electrons have I drawn total? 8. Okay, so there's 2 more that I can draw. And those 2 more that I can draw, go ahead and put 4 in the chat if you think that I should draw a quadruple bond, or a 9 in the chat if there's no such thing as a quadruple bond. Perfect. There's no such thing as a quadruple bond. It's a neat idea, but no. So these extra electrons. First question is, does carbon have a complete octet? It does. Does nitrogen have a complete octet? Does not. So what do I want to do? Well, I'm going to put a lone pair of electrons on nitrogen. Does nitrogen now have a complete octet? It does. So I'm going to erase the structure that I just drew, and I'm going to put these electrons right here. Now, one of the things that's could everyone give me a 5 in the chat if you follow that. That's our high fives that we just gave each other, everyone. Okay. So there's our Lewis structure of HCN. We've got that lone pair of electrons out there by nitrogen. Now, one of the things that's important to know when it comes to VSEPR theory and molecular shapes is those two electrons that I just drew to get us to a grand total of 10 electrons for this structure. Hate to say it, but they don't matter. The reason that they don't matter when it comes to designating the molecule shape is because the only electrons that we care about, oh, dang it, thought I had a mosquito. The only thing that matters when it comes to that molecule shape, is it wrong to put the pair of electrons? Oh, is it wrong to put the pair of electrons on carbon? Absolutely, it is. Just so we can kind of visualize that. Sorry to. How many carbons does carbon now have? 2, 4, 6, 8, 10. So carbon exceeds the octet. Whereas when we put them out here by nitrogen, 2, 4, 6, 8. Nitrogen has a complete octet. Thank you for asking that question because I know that you are not the only person who had that question. But when it comes to designating molecule shape, we only care about our central atom. And we care about the electrons on that central atom. And so we have this designation where we say A. Our central atom is represented by the symbol A. Could everyone add to the chat the letter that represents our central atom anytime we're doing VSEPR theory? Great. Okay. And then the next thing that we do is we represent adjacent atoms. So those that are off of our central atom with the letter X. Now, the last thing that we're going to do is we are going to put a subscript to represent the number of adjacent atoms. Could anyone add to the chat the number of adjacent atoms that are basically bound to our carbon? 2. So this would be an example of AX2. Can you give me a Y in the chat if you follow that and N in the chat if you do not follow that? Okay. Now, what we're doing is anytime that we come up with a Lewis structure, we want to figure out how it fits with or represent it with this model that's known as the AX model. So A represents our central atom, carbon. X represents the adjacent atoms. And then the 2 represents the number of adjacent atoms. So we have A, basically A, X, X. And we can simplify that into AX2. Now, all of this is about, well, these electrons, they're repelling one another. Okay, so we've got a triple bond and a single bond. We don't care that this one is a triple bond and this is a single bond. These are electrons that are repelling one another. And most importantly, these are shared pairs of electrons. Now, with that in mind, the way that I think is helpful to visualize this is to treat this as, all right, well, we have, okay, so if these electrons that I'm going to put a smiley face on, if these electrons push these electrons that I'm going to put a frowny face on, well, these electrons with the frowny face are kind of going to also be pushing away the electrons that have a smiley face. Could anyone give me so like they are repelling. So just as the smiley face electrons are repelling the frowny face electrons, or the H to C electrons, I won't do smiley faces. Just as the H to C electrons are repelling the C to N electrons, the C to N electrons are repelling the H to C electrons. Can you give me a Y in the chat if you follow that? Okay, great. So these electrons say, I want to be as far away from you as you want to be, or as possible. And the other electrons are saying the exact same thing. So What that means is that even though this is in 3 dimensions, these will be 180 degrees away from one another. So this molecule is known as a linear molecule. So no matter where these electrons kind of migrate, they will all be pushing away one another. Now, when we go down to this molecule down here, could you give me in the chat the AX modeling of this molecule? And you don't have to do a subscript. So A is our central atom, and then what do we do? AX2. Great. Okay. Now, let's take a moment and build on that, though. So AX2 represents A, X, X. So we got two adjacent atoms. What makes this figure up here this different from the one on the bottom? Well, our central atom has one, two, the lone pairs. Absolutely. So what do we do to kind of clarify that and represent these differences? We use E, AX2, E2. Why is it E2? Well, there's two lone pairs of electrons. Okay, can everyone give me a Y in the chat if they follow what the E represents? The E represents lone pairs on the central atom. Okay, so if you wanted to kind of do an inventory of the A, the X, the E's, you could have just written AX2E0 because there are 0 lone pairs on our central carbon here. But rather than writing E0, we just leave it off altogether. Now, with that in mind, what we usually do is we look at the central atom and say and refer to electrons, whether they are bonded or non-bonded, or shared, I'll say shared, or unshared electrons. And we refer to them as electron domains. Okay. So looking at HCN, this is one domain, and then this is a second domain. Could anyone tell me how many domains, how many electron domains surround the oxygen in water? 4. Could anyone tell me the number of electron domains that surround carbon in CH4? 4. NH3. How many electron domains? It's 4. It's a little bit tricky, but it's 4 because we don't care if the domains we don't care if the electrons are shared or unshared. We look at this and we say 1 domain, 2 domains, 3 domains, 4 domains. There are 4 basically groups of electrons around our central atom. Can everyone give me a Y or an N in the chat if they follow that? So when we see a structure, great job, everyone. Thank you very much. When we see a structure, we want to count up, well, how many domains are there? And after we answer that question, we want to say, well, are these domains different at all? Could anyone give me the AX designation for CH4? We've got 4 domains. How many lone pairs and how many shared pairs of electrons are around our central carbon? AX4. Wonderful. What about for NH3? AX3E1. And you might see this written as, rather than E1, just written as E, because, well, if there is no E present, that means there's no lone pairs of electrons. If there is an E present and it has no number, that just indicates that there is one lone pair of electrons. Okay. Can you give me let's go with a 1 to 3. 1 with, hey, I feel pretty good about using the ax designation. And a 3 being, I'm still having trouble with that, and I'd like to see some more examples. And I know this is tricky just because you're taking a symbolic representation and then you're coming up with another symbol. But we'll get there. Okay. So Vesper theory is a way of looking at what a Lewis structure is and what electron domains are around our central atom and how those electron domains behave around one another. When we look at something like AX2E2, any molecule that has that designation is considered a bent molecule because it has two lone pairs of electrons and two adjacent atoms. These lone pairs of electrons, represented here and here respectively, what they are doing is they are occupying as much space as possible. And so what they're going to do is they're going to be pushing down against the shared pairs of electrons. And so what we do is we look at the bond angles. Okay, now I want to show you this next table, and we're going to look at different aspects of it and different elements of it. So if we look at this right here, our first column, that gives us our numbers of domains. We just looked at HCN. That would be an example of a molecule that has two domains. It had two adjacent atoms. So we had A for our central atom, and then X, 2. This table breaks it down into number of bonded atoms or lone pairs of electrons. Now, the only kind of configuration that can exist when you have two adjacent atoms is, well, a linear molecule. So AX2. There is no such thing as a molecule that is AXE. So a double or triple bond is considered one bonded atom. Yes, I'm happy that you asked that, because this triple bond, we kind of treat the same as this single bond in terms of how much these repel one another. It's a great question. So if we were to look at something like carbon dioxide, I'm going to draw carbon dioxide, and then what I want you guys to do is, actually, I'll do it right here. Or I'll do carbon dioxide in just a moment. So this would be AX2. AX3 is where a central atom has three bonded electrons, or three bonded atoms. Then AX2E is where we have two adjacent atoms and then one lone pair of electrons on that central atom. Then AX4, AX3E, and then last but not least, AX2E2. Now, what I want you guys to do first is tell me how many lone pairs of electrons are on the central atom in the AX3E1. How many lone pairs of electrons are on that central atom? 1. Great. How many lone pairs of electrons are on the AX2E central atom? Perfect. Now, look at this table for a moment. Does anyone see any of these configurations, add a Y or an N to this, where your central atom has one adjacent atom and three lone pairs of electrons? No. we're always focused in on our central atom. Now, with that in mind, I want to show you this compound. Um, see, what I would like you guys to do is tell me the molecular or tell me first the AX or the AX configuration of this molecule. AX2. Okay. Kelly, I like what you did there. But just a little bit of a kind of reminder, we are focused on our central atom. Our central atom is our A. Our adjacent atoms, in this case oxygens, represent our X's. So we have two X's. We then want to say, okay, well, what about our E? How many lone pairs of electrons are on that E, on that A, basically, on that central atom? Well, there aren't any lone pairs. So that'd be zero, which we can then basically erase. Now, what that means when it comes to designating our configuration with this VSEPR theory, it doesn't matter what our adjacent atoms have. So basically, we just look at it and say, okay, well, we've got how many bonds coming off of it? How many lone pairs of electrons are on that central atom? Can everyone give me a Y or an N if they follow how CO2 gets AX2? Okay, great. Now, the next one that I want to go to is I gave you guys CF4 a little bit ago. And you know what? I'm going to give myself, I got to adjust my slide deck here to give myself a new blank slide. And that is present now. So I'm going to go ahead. Here we go. We're going to work through CF4. Carbon rolls in with 4 valence electrons. Each fluorine rolls in with 7. 7 times 4 is 28. So we got a grand total of 32 electrons to draw. Can everyone give me a Y or an N to the chat if they follow that they understand where, yeah, all these electron total numbers came from? Wonderful. So we've got these valence electrons to draw. Our central atom is our least electronegative element. It's our first element listed, and it's the one farthest to the left. Well, fluorine is our most electronegative element, so anything but fluorine. And so we've got C, F, 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 F. Is everyone good with that setup? Y or N to the chat. Single bond, single bond, single bond, single bond. That's 4 single bonds, so that gets 8 electrons out of the way. So 32 minus 8 gives us 24 electrons left. So 24 electrons. That's what I have left to draw. Could everyone give me a 5 in the chat if you follow that? Okay. So I'm going to go around each one of my fluorines. 1, 2, 3, 4, 5, 6. This fluorine, does it have a complete octet? Add an 8 to the chat if it does. So I'm going to go ahead and, yep, you're all right. Do the exact same thing to all of them. And then what I'm going to do, complete my octet, then I'm going to take stock of all my electrons. So I had 24 to draw. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 24 electrons. That's what I had left to draw. That's what I drew. I'm going to erase this, erase this, erase this. Done, done, done. Dun 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 dun. Done. So 24 minus 24 gives me 0 electrons. Does everyone agree with this structure? Give me a, yeah, YRN in the chat. Perfect. Now, could anyone give me the AX designation of this molecule? Done. Yep. AX4. Because yeah, fluorine here, oh man, that's three lone pairs of electrons in one adjacent atom, but we don't care about fluorine. We are writing this in a carbon-centric way. What if I change this to CHF3? Ooh, well, I'm gonna change this. So that changes what we've got. Our total number of electrons, I'm gonna adjust this. Um, we've got 7 times, I'm gonna erase all that math. Change that to 3, and then I'll put the H right here. 1, 3, 21. So we're looking at 26 electrons. Does everyone follow where all that came from? Give me a Y or N to the chat. Okay. So H. Does this hydrogen now have a complete octet? It doesn't have 8 for its octet, but it's happy. It wants 2 electrons. It's got those 2 electrons. So I'll do 26. That was my total number of valence electrons to draw. 26 minus 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 minus 26, 0. Now, give me the AX designation for CHF3. AX4. Yep. The central atom is still carbon. It's got 4 adjacent atoms. CHF3 is still AX4. Okay. Now, what I want you guys to know is I want you to be able to use this information on this table. Now, with that in mind, you have to know a couple of things. When you see a figure, what I want you guys to be able to do is if I give you a molecule's formula, I want you to be able to process that. So that means kind of sketch out the Lewis structure and then look at it and say, okay, well, how many bonded atoms? Does it have 2, 3? Does it have 4? And then how many lone pairs of electrons are on that central atom? Then I want you to know these names. So if you have a molecule that has 2 bonded atoms, it is a linear molecule. If you have a molecule that has 2 bonded atoms, 1 lone pair, you've got a bent molecule. 2 bonded atoms, 2 lone pairs. That is also a bent molecule. If it's 3 bonded atoms and no lone pairs, that's a trigonal planar or trigonal planar. I pronounce it trigonal. I don't know why. I don't think that's not correct. It's a tetrahedral molecule. If it has nothing but 4 atoms coming out of it, it's a trigonal pyramidal. If it's got 3 bonded atoms and 1 lone pair of electrons. This is all information that I want you guys to know. Does everyone follow that? Do you think that, or give me a Y or N if you follow this. Great. Do you think on a Y or N to the chat, do you think that this would be something that would be good to put onto your note card? Yeah. Some of them, no. Like linear, for instance. AX2. What I would do is I would just write this down as, let me erase that. I would say AX2, linear, 180. AX3, trigonal planar, 120. AX2E is bent, 120. You could treat it almost as, well, how many domains does it have? If it has 3 domains, it's 120 degrees is our bond angle. If it has four domains, our bond angle is 109.5. So AX4. Then there's that. AX3E and then AX2E2. Can you give me a 9 in the chat if you say, oh, I got that. I can do that. Can you give me a 7 in the chat if you think, hey, you know, this seems like kind of straightforward? Can you give me a 3 in the chat if you think I could get from a Lewis structure to the bond angle? I might, I'm going to reference uh my note card, but that's what it's there for. Okay, cool. I'm seeing some numbers that aren't the 3, 7, or 9 or the 5, but that's fine. This would be a good thing to throw down on your paper, so keep that in mind. Okay, now we've got our first poll question. Poll, and it is up. In the AX system, what does the E stand for? Why hasn't hydrogen the central atom, or why wasn't hydrogen the central atom for the new compound since it's the furthest to the reason, okay, I'm happy that I was asked why wasn't hydrogen the central atom because it's farthest to the left on the periodic table. The reason is that hydrogen's always kind of like an exception. Hydrogen only wants 2 electrons. If hydrogen is the central atom, it's immediately going to exceed the octet. Because if we were to say like I think the molecule that we're referencing was this CF, or, so hydrogen always kind of treated as an exception, CHF3. If we had hydrogen in the center and we had carbon, if we had something like that, well, this hydrogen, how many electrons does it see? It has 8. Hydrogen only has room for 2 electrons because hydrogen only brings in 1 valence electron. It's a great question, though. But I would always, one other thing that I'd put on my note card is hydrogen likes to be an exception, or hydrogen doesn't follow the rules. Give me some sort of code like that for myself. Okay, so the correct answer for this question was pair of electrons. Absolutely. So I'm going to end the poll. Great job, everyone. Next up is we've got another poll question. And that poll question reads, which of the following atoms is which of the following, atoms is AX2E2? So this is the sort of question that would be a good one for like going through the whole process. So what I'm going to do is what I'm looking for is something like this. A, X, X, and then boom, boom to represent my lone pairs of electrons. Okay, so now what I'm looking at is, well, I'm going to draw each one of these. CO2. Okay. Now, carbon rolls in with C has 4 electrons. Each oxygen has 6 electrons. So that means we've got 4 plus 12 equals 16 electrons total to draw. Our central atom is going to be carbon. There's my starting point. Now, after that, I'm going to complete my octet for my adjacent elements. And then I'm going to complete my octet on my central element, which is oxygen, or carbon, sorry. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So 20 electrons. So this is a structure that presents a little bit of a challenge and a little bit of a problem. So now what I want to do is if I've drawn too many electrons after everything has a complete octet, then I want to go on to, well, adding double bonds. So if I added a double bond here, well, then I need to, for each double bond, I want to erase a lone pair on my central atom. So now the question is, does carbon have a complete octet as this is drawn? It does. Do each of my oxygens have a complete octet? Well, they exceed the octet. How many total electrons do I have drawn? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, okay. Well, I removed my lone pair on my central atom, but I didn't really resolve the issue of too many electrons. So now what I need to do is erase on my adjacent atoms because that double bond is being shared. So those electrons count for both of the atoms that are counted or are bound to it. So 2, 4, 6, 8, 10, 12, 14, 16. Aha! This is my structure. So this would be AX2, H2O. Well, oxygen, hydrogen, hydrogen. Oxygen's rolling in with 6 electrons. Each hydrogen's bringing 1 electron. So we've actually got, that's 4, 6, 8. Ooh, that's our AX2E2. Last but not least, I'm going to do all of them just so you guys can see this all played out. CH4. Well, this is our classic. This is what we started the class with. Each hydrogen brings 1 valence electron. Carbon brings 4 valence electrons. So CH4, 2, 4, 6, 8. 8 electrons. CH4 is good to go. Last but not least is NH3. Nitrogen brings 5 valence electrons. Hydrogen brings 3 total. So you've got N. That's 6 electrons drawn. Nitrogen does not have a complete octet. Then when I add a lone pair, now it does. So AX3E. Could everyone give me a Y or an N to the chat if they followed kind of breaking down each one of these and kind of converting it to the AX model? Wonderful. Well, I'm going to go ahead and end the poll there. Now, this is all important stuff to be able to convert this. But what it also plays into is one of the topics that we talked about. We talked about bond polarity. Could anyone tell me, it's a word that starts with E, what is the kind of property that relates to bonds and polarity? And it's a number, quantifying the number, or quantifying the kind of pull that each electron or each atom has. Starts with an E. Electronegativity. Wonderful. Electronegativity is going to give us an idea of, hey, is this bond polar? Now, with that in mind, this is an important thing to know about on this next slide. If a bond is polar, okay, cool, does not mean a molecule is polar. It's kind of like a little bit of a, I don't know, it's complicating. It complicates this idea of polarity. Chemists classify compounds as being polar or nonpolar. Polar, nonpolar, and ionic compounds. That's how we classify things. Now, we can use electronegativity to indicate if a bond is polar, but that doesn't necessarily mean that our molecule is polar. Now, in this figure right here, add to the chat, which one of these elements, A or B, if we've got this representing our polarity, A or B, which one of them is more electronegative? B, spot on. And one of the ways that I know that I mentioned, the way that I always kind of like to visualize it is this kind of positive or this cross end of this dipole, that's more positive, so it's closer to this. So the less electronegative element. So B is more electronegative in this molecule right here. In this bond right here. Now, when you look at compounds like this, well, you want to classify, is this a polar molecule or a nonpolar molecule? Now, with that in mind, sorry, just a second. We're asking the question, well, are we having electrons kind of gravitate in this direction or in this direction? And in this case, we've got two molecules, both here, both of these are polar. And the reason that they are polar is kind of two different reasons. Well, HCN is a polar molecule because N is more electronegative than carbon. And so let's say if I were to, let's see, I think that the electronegativity for nitrogen, let's call it 3.5. And carbon, let's call it 2.8. Okay. Then this would be, okay, so no, I'm gonna erase those. I don't want to put the wrong numbers and get it wrong. What we have here, though, is if we split this molecule down the middle, is what is on the left-hand side of the central atom and what is on the right-hand side of the molecule, is it identical? Y or N to the chat? No, it's not. When something is not the same on each side, we talk about symmetry. So this molecule is not symmetrical because on the left-hand side, we have a hydrogen. On the right-hand side, we have a nitrogen. So this is an asymmetric molecule. Asymmetric. Can you add a Y or an N to the chat if you follow that? Okay. Now, let's go back to our example, and I'm going to have to do a little bit of work with it. I'm fine with that. F. Okay, so if I split it like this, is this molecule symmetric? Yeah. Okay, if I were to change the axis and go like this, is it symmetric? And not from an artist standpoint, but yeah, it is. Even if we talk about this in 3 dimensions, this molecule, CF4, on each side of that carbon, you've got symmetry. All of these bonds are symmetrical. And so just based on the electronegativity of carbon to fluorine, do you think, and fluorine being our most electronegative element, add a 1 to the chat if you think that this bond that I've circled, just the bond, do you think that bond is polar? Do you think the electronegativity difference between fluorine and fluorine and carbon is greater than 0.5? Yeah. Okay. Now, what about, I'm going to circle this bond right here. Do you think that that bond is polar? Y or N to the chat? Yeah. As you can kind of see, and as everyone's kind of anticipating, I'm drawing 4 bonds that are all polar. Would everyone agree that these bonds are all polar? They're all identical. Now, let's say to draw kind of a visual of this. This right here is me, Joel. I'm gonna put a little dot in the middle, and then over here, I've cloned myself. I didn't tell you guys, but this is also me. And then this is also me. And then this is also me. The reason that the one in the bottom is apparently smaller is just perspective. So okay, so that's me. And let's say that the 4 Bs, we're playing a game of tug of war. And we're all pulling. We're all equally strong. We all go to the same gym. It's really nice. We can distribute the costs. We all have 4 separate jobs. Um, and so we go in, we work out, we're all super strong. Um, who's gonna win this game of tug of war? If it's one of the me's, put a 1 in the chat. If it's none of us, put a 0 in the chat. Yeah. So if we had like this little dot that I've got in the middle, that's not going anywhere. Let's say, and so think about our strength as our electronegativity. Now, let's say that one of the me's is replaced, and yes, I am drawing a different stick figure to represent a different person. Um, and let's say that we replace this with let's go with hmm, I'm gonna go with let's see, Peyton Manning. Um, I'm not gonna say that I'm stronger than Peyton Manning, but I am gonna say I'm younger than him. And so that should count for something, I think. I don't know. Um, let's just imagine that Peyton Manning is stronger than me. Let's hypothesize in this crazy world that Peyton Manning is stronger than me. Um, is somebody going to win this game of tug of war? Add a one to the chat if yes, somebody is, and a zero to the chat if no, nobody's going to win this game of tug of war. You're right. Somebody is. It doesn't matter if Peyton Manning is stronger or weaker. If I replace this Peyton Manning with instead um, Arlo Gray, somebody's proposing Ray Lewis. Okay, yeah. Arlo Gray, my 5-year-old. Um, he is very strong at his own declaration, yet he can't pick me up. Is somebody going to win this game of tug of war? One to the chat if yes, zero to the chat if no. Nobody's going to win. You're right. Somebody is going to win it. It doesn't matter that the three me's are stronger than Arlo. It wouldn't even matter if Arlo is stronger than the three me's. The point is that there is some differential in pull. So my point here is that when you have a symmetric molecule, you have a non-polar molecule. Symmetry equals non-polar. And the way that I would suggest kind of translating that is to say non-polar means nobody wins the game of tug of war. Could you give me a 5 in the chat if you follow that? Okay. Now, if symmetry means non-polar, then what does asymmetry mean? Well, that means polar. Your molecule is polar. Okay, so what I'm getting at and what I want you guys to know is electronegativity is going to determine if your bond is polar. It's not necessarily going to dictate if the molecule is polar. Okay? When it comes to determining if a molecule is polar or nonpolar, we've got to look at that molecule, which is why we look at all this stuff right here. Tell me, is this going to make a polar or nonpolar molecule? Add an N for nonpolar or P for polar. This molecule right here, we've got this and this. They're pulling with the exact same strength. So they will cancel out. So this would be a nonpolar molecule. So did I say? Yeah, symmetry is nonpolar. Okay. Sorry, I see lots of P's in response to that, but AX2, non-polar. Does that make sense? Give me a Y or N to the chat. Okay. Now, let's go with the next one. We've got AX3. Okay, an important point about this. And look at this as your model. Okay, we've got our bond angle 120. But when we have an AX3, we have one, two, three different things, or three identical things that are pulling with the exact same strength. We've got something that is non-polar. I think I was confused because CHN is linear, but it's polar. Okay, I understand. So I'm going to come back to this. So this is sort of a general rule. Thank you very much for the private message. When we look at AX2E, we know without a shadow of a doubt that this is going to make a polar compound. There are no exceptions to this because of the fact that we have one lone pair of electrons. As soon as you put a lone pair of electrons on there, you know that that's going to make a polar compound. So you can look at, let me go ahead. Sorry, I need to erase those two. What I just wrote was true about 9 out of 10 times, but not 100% of the time. What I'm going to write now is going to be basically 100%. Sorry, I can even remove the basically. 100% of the time. If you see AX3E, that's a polar compound. If you see AX2E2, that is a polar compound. Now, I'm going to jump back to this right here. This would be AX2E2. We know that this is a polar compound. Yeah, it's water, but these two lone pairs of electrons, depicted here and here respectively. Think about those as those are like spheres or balloons that are kind of in constant motion. So it doesn't matter how polar this bond or this bond is. These two lone pairs of electrons are just wild hairs. When you see a lone pair of electrons on there, that molecule is going to be polar. Now, can everyone give me what I've got right here with polar and not designated? Can you give me a 1 to the chat if you follow that? And a 2 to the chat, or a 3 if you don't. Okay. All right. Now we've got what I think is our last poll question. Using the AXE system, how would you best describe CH4? We got a central atom. We got 4 adjacent atoms. Okay. Now, I'm going to go ahead and go on to our next slide. Let's see. Okay. So I'll leave the poll question up. What we're looking at is central atom. AX4. That's what we're looking at. Now, when we classify a molecule, if we have a lone pair of electrons on our central atom, it is absolutely going to be a polar molecule. When we don't have a central, or we don't have a lone pair of electrons on our central atom, we have to be thinking about what is on there. So HCN, that is an exception. So AX2, I want you to look at that and think, chances are it's going to make a polar or a non-polar molecule because our adjacent things, as is the case with CO2. Our oxygens are basically pulling with the exact same strength, so they'll cancel one another out. Well, if this is not oxygen on each side, then you have a polar compound. It is asymmetric. So look for symmetry and look for lone pairs of electrons. Now, BF3 has the same bonded atoms and does not have a lone pair of electrons. This would be AX3. This is AX4. If you switch this from BF3 to, well, this molecule, add to the chat with a P or an N. Does this modification make our molecule P for polar or N for nonpolar? That minor change that I just made, switching one of the fluorines to a hydrogen. Absolutely right. I got rid of the symmetry by replacing one of those fluorines with a hydrogen. Therefore, I've made this molecule a polar molecule. So this is polar. But then whenever I revert back to BF3, that would be a non-polar molecule because all of the outside atoms, all the adjacent atoms are identical. Okay, well, that's what I've got for the day. I'm going to end the poll and I'm going to stop the recording